Recording has started. So if I recall, the recording doesn't capture the whiteboard. So I'm going to share my screen and bring up the assignment and paint. Given a number of 4 controllers with the following oscillators and drift rates, what is meant by convergence function? You don't actually need any of this information to know that. Convergence function is just the sort of leftover bit of time after synchronization that depends on what synchronization method you're using. So anything like that, probably get credit for. Next part you do need the numbers for. Given a maximal allowable precision of 4.5 times 10 to the negative fourth seconds per second. Well, no, that's not right. Precision is in seconds. The drifts are in seconds per second. And a convergence equal to 0, what is the maximum resynchronization interval required? Okay, so formula from the notes says that your convergence function plus your runaway drift needs to be less than or equal to your precision. So if your precision is convergence function is given as 0 plus gamma must be less than or equal to 4.5 e negative 4. So you can sort of get rid of that. And so gamma we know is the rsync interval times how often how much your clocks drift. So you want to pick the most extreme clocks. So the most extreme clocks here are the 100 parts per million. So that's times 10 to the negative 6th plus 120 times 10 to the negative 6th. And so that's 220 times 10 to the negative 6th. So if you divide both sides by that, e to the negative 4th over, that's one of the nice things about the whiteboard is it automatically extends for you. So divide this by 220 e to the negative 6th. That makes that positive 2. So 450 divided by 220, 45 over 22, something like 2 seconds. A little bit more than 2 seconds. So anything like that, show your work, should get full credit. So can I just hit Control N to get a new one? Yes. Okay. All right. Problem 2. Well, I guess any questions about problem 1? We'll take those one at a time. Oh, we had a 5th person here. Maybe they knew everything. Any questions about problem 2? Or problem 1? Okay, we'll go back to problem 2. So problem 2, the time counters in the columns table represent the time particular node transmits to another node. For instance, node 2 receives the time 502 from 1. Okay, so identify from the table the Byzantine node clock and why. So that would be the one that sends different numbers to different clocks. So all the same, all the same, all the same, all the same. Number 5 sends different values to different clocks. All the same, all the same. So number 5 is your Byzantine node / clock. Suppose all the nodes apply the fault-tolerant average method for internal synchronization. Determine the corrected time for nodes 3 and 7. So we will do node 3. So the time on node 3, according to node 3, is 4:58. So Clock 1 is, plus 4. Clock um, 2 is plus 10. Clock 3 is, itself, so it's 0. Clock 4 is plus 3. Clock 5 is minus 8. It's one of those Byzantine ones. So that's why that one's going to be different for 3 and 7. That's why the FTA is not going to be the same. Clock 6 is plus 8. And clock 7 is plus 6. So get rid of the two most extreme ones. And don't technically say k equals 1, so if you didn't get rid of any of them, probably okay. You just got to make sure you're dividing by the right amount if you don't get rid of those. But we do have a Byzantine error, so you probably should, get rid of 1. But now there's 5 things left, right? So, sum of this divided by 5, 0 plus 3 plus 4 is 7 plus 6 is 13 plus 18 is 21. 21 divided by 5 looks like that should be an offset of like 4.2. So the corrected time goes from 4:58 to 5:02.2. I think that's right. Any questions about that? I mean, I'll go through note 7 as well if you want, but it's the same way. You do it the same way. Value is different because of the Byzantine error, but the method's the same. So does everyone understand how applying the FTA works there? All right. Number 3. So given the latency jitter of 15 microseconds, let's clear this. What is convergence function? So if you're using the central master method, then latency jitter is convergence function. So it would just be 15 microseconds. If you're using some other thing, it's always going to be at least as much as, the jitter. So, if you said 15 microseconds, you should get full credit. If you said, if it's the central master method, 15 microseconds, you should get full credit. If you said something like, jitter plus a constant, that is probably even more correct conceptually. Although we really didn't talk about jitter vis-a-vis, FTA or something like that. But technically, there is some time that, if you've got to send all the, clock times from each clock to every other clock, there could possibly be some delay in there as well. So, that could be the case. So, given your answer for part A, so we know that the, convergence function is going to be something like that. Then if you know that convergence function plus gamma is less than or equal to precision, just like before, then if we know the rsync interval, so we know gamma is, the drifts times, rsync, and we know rsync is 2, and we know that convergence function is something like 15 times 10 to the negative microseconds is -6. Plus. Then if we have clock drift rates of 10 to the -5th seconds per second, then we have to take 2 extremes. So we have to take both of them. So this example is sort of the 2 times 1, 10 to the -5th. So the best precision, would be, the worst case precision would be when these things are equal. So if we just do the math here, 2 times 10 to the negative fifth times 2 is 4 times 10 to the negative fifth. I don't know why that's on there. That's captured by the E. You know, plus, 1.5 times 10 to the negative fifth, so you end up with 5.5 times 10 to the negative fifth. That sounds right to me. Something like that. I could double check my key, but I want to bring it up on screen. So I'm going to trust that I did that correctly, or plus a constant, if you included all that in there, so if it was, 5.5 times 10 to the negative fifth plus a constant, that's also correct. The last two are writing things, so, I'm not going to cover that now. Any questions about problem 3 from the handwritten assignment? If not, then we will jump into the programming challenge. So this is my solution, not too bad. We're going to put in a breakpoint. We're going to walk through this. So, and then let's go back to the website next to make sure we read things you want. So, assuming a convergence function equal to 0, and given a precision requirement of 0.5 seconds and the drift rate results from module 3 provided in row solution, compute the resynchronization interval. So, let's start this. We load in the clock times, load in the rows. You see the rows are here. They're signed, so that means we can, just go ahead and just grab the largest and the smallest one. So those will be our 2 extreme rows. This says gamma. Technically, that should be probably pi because that's the precision. So your resync interval is going to be your precision divided by, just like from the homework, the absolute value of the 2 extreme drift rates. And so we get an rsync of 1.3164. So compute the resynchronization interval for part 1. Your answer should be something like 1.3164. Write a function that implements the fault-tolerant averaging in MATLAB. So actually, I did that in a separate file. So this is going to take the time for a specific clock and the time for all the clocks. And this one is actually fixed for you. If you parameterize this and just took the number of Byzantine errors, that's better. This is doing a fixed 1. So we're computing the offsets. Because obviously you've got to calculate for all of them. So if you just take all the clocks minus this clock, you've got all the offsets. If you do that in a loop, that's fine. But remember, we're in MATLAB, so you should be thinking, array-based. Sort them. There is a built-in sort function in MATLAB. So now we've got the sorted offsets. And so if we want to get rid of the smallest one, the biggest one, we can actually just take everything except for the first element and everything except for the last element in the sorted array. So you don't actually have to walk, if you're thinking about this from a CS, from a C++ perspective, you might think you need to walk the array and put in a different array where you ignore those things. No, you can just, pull out the elements directly. So now we've got just the offsets we want. So we want to take the average of that. And so we take the mean of, everything except for the largest and the smallest, and that is the FTA offset we're going to use. So that is our implementation of the fault-tolerant averaging method. So that's part 2 done. So now we want to apply the fault-tolerant fault-tolerant averaging method on the clock-time.mat data every resynchronization interval. So how are we going to do that? This one can be a little trickier to implement. But you'll notice here, we're saying, okay, so we know the start time is. We know we want to resync after the resynchronization interval. So we're going to have this variable that is, the next time we resync. That's what time to sync is. So we take the first time, add the resync interval. And so then here, I'm store extra copies of the clocks. You probably don't need to do that in your implementation. I do that here just because I put in some extra graphs demonstrating how the algorithm works, and so I needed to keep the original values. So your solution could be, 7 lines shorter than mine there. So for every value in the clocks, from 1 to the end of the clocks, if we have reached our resync point, so if the current time in the reference clock is greater than the resync point, and if you said T1 instead of Tref, probably not going to take off points, but really should be using the reference clock for that sort of thing. Then we're going to grab the current. Sure, that's not stepping. Oh yeah, it's because it's not hitting that. So let's go into, okay, so grab the current slice of times. So we're going to get the current index for clock 1, clock 2, clock 3, clock 4, clock 5, clock 6, clock 7. And then we're going to calculate what the offset is. Now there's no Byzantine errors here. So really, that average part's going to be the same for all of them. But so maybe you could have done this slightly more efficiently than I did. But this is just doing it all independently. So we apply the FTA method on clock 1's time for that entire slice, and then, and this is the tricky bit, we apply that offset to all future values. And so if you did it on all values, your final plot would just look straight. If you did it just like you did on no values, just be like offset slightly. If you only do it on the current value, then you're going to get like straight lines with like 7 spikes in it. If you saw that, that meant you were just applying the resync just at the resync point and not all future values. And so, again, the C++ programmer might do this in a loop, but we can use arrays. We can just say, oh, every value from now to the end of the array, add the offset to it. And that automatically does all of them. And then update our time sync point to be the current time sync point plus the next resync interval. And then this will keep going through the loop until it hits that again. It'll calculate new FTAs and it will do it again. So get rid of this breakpoint. We'll start plotting some stuff. Okay, so this plot isn't the answers. Don't be confused. This plot is helping you visualize how the algorithm actually works. So we're going to make a plot. We are going to plot the new values for time 1. So this is just what the time 1 looks like. Obviously for you, you're going to have all 7 lines in there for your real plot. But you can see it goes, then it gets resynced, then it goes, then it gets resynced, and it goes, and it gets resynced, and so on. Now, this is more useful if we actually compare this to the reference line. So now the straight line, and I'll make this bigger. The straight line here on the diagonal is the reference line, and so the time 1, because this clock is slower, since on this side of maybe that's faster because I don't have my axes on there, so I can't quite tell. If I have my axes labeled, I'd know. But either way, since I'm on this side of the reference line, when I resync, I always go towards the reference line. So this one, if it's drifting this direction, it's always going to have to be redrifted back in that direction. I guess if you had wild swings in your drift, the direction would change, but always go back towards that the center line there. And then just to prove that, I put a third line on there that is the actual time 1 line. So you can see if you were just plotting time 1, it would be that green line there. But so at first it is just that green line. Then you get a resync, and then it is parallel to that green line, resync parallel to the green line, resync parallel to the green line, resync parallel, and so on. And you'll do 7 of those for your actual plot. So then we will go ahead and step through here. And if you didn't put the reference line on there, that's fine. But there's your reference line. There's line 1 we just saw. There's, top one, that one was above the line, goes back towards the line, and so on. And once you've got all 7 of them, we'll go ahead and put the labels on there too. You should end up with something like this. You've got your cluster of lines spreading, converging, spreading, converging, spreading, converging, spreading, converging, spreading, converging, spreading, converging. And so if you've got your rsync interval right, you should have 1, 2, 3, 4, 5, 6 resync points through your plot there. So, any questions about the programming challenge? Okay, any questions about anything else in general? Obviously, we'll have a review session next week. I think there might be exactly one question on the next homework, plus a writing portion. I can't quite remember. So that'd be a fairly short meeting. There's something else I wanted to say. Can't remember what it was, though. But if there's nothing else, then I will stop screen share. Oh, here we go. Is there some way to see if the whole ensemble will be faster or slower than the reference plot clock? If all the drifts have the same sign, then that would mean the entire ensemble is going to be slower than the reference line. Yeah, and so since they're resyncing off of each other, you're still going to end up with something that is going to keep being to one side of the reference line there. Yeah, I guess sort of the FTA has this built-in assumption that your clocks are decent, that there's a good statistical sampling of the error rates. But yeah, if you all had something, and obviously, we've been specifying the drifts in plus or minus parts per million. Yeah, so if they were all drifting slow, then do I have a good way to visualize that? No, because that data is built into the clock time. I can't just change the drift rates. That's a good question though. Yeah. So the the FTA is only as good as your clocks. If you have all bad clocks in the same if you have all the same bias, you're still going to drift outside that precision eventually, I think. Let's think how that math would work. So you're saying the resync interval is going to be precision divided by this thing. Yeah, you may end up with a negative time for your resync interval. So what does that mean? It means you need to resync infinitely. You need to go back in time and resync your clocks. So that would be an example of when the FTA method might fail. That could be a good exam question in the future. I'm not going to put on the exam this time. Maybe. I'll think about that some more. That could be a good question to put on there. And see if people are watching these recordings. Because that's no. Well, because I tell people that all of the content of the exam comes from the slides and the homeworks. But I guess that is just a I guess that falls directly out of the equation though. If you have clock drifts that can make your rsync negative, what does that mean? So that might, I haven't made the exam yet, so that might show up on the exam. So that's a good question. Any other questions? That was a good one. Yeah, I guess there'd also be a fault in the rsync equation there if you had clocks that we put the absolute value in there, but if we didn't, if we said that one clock was drifting, exactly 20 parts per million faster, and one clock was drifting exactly so let's say both your clocks were drifting at the exact same rate. Then you also then you'd have an rsync interval of infinity. You'd have divided by 0, in your equation, so you wouldn't be able to those clocks wouldn't be able to help each other. Obviously if you had 7 clocks, they're all drifting at exactly the same rate, plus or minus, that would also be a special case in the equation there. Not much you can do about that. But yeah, that's a good thought experiment. Any other questions before I stop the recording? Okay, then I will stop the recording.